In this video, we are going to learn the Bernoulli rule type 4. Sometimes the Bernoulli rule also called the L'Hopital's rule due to a historical mistake. But we are going to call this Bernoulli rule. The reason is, it is Bernoulli who came up with the idea. And the result was published later in L'Hopital's book. So we're going to study a special type in this one. So like another indeterminate form. So we're going to study what will happen to the power function. So we have when x goes to a can be a finite number infinity. You have powers fx to the gx, fx to gx. So when you have a power like that, several things can happen. So you can see that you can get 1 to infinity, 0 to infinity, infinity to 0 and 0 to 0. But out of those you can see that 0 to infinity is clear because when you have a small number, when you raise to the larger power, it automatically goes to 0. So that's 0, that's clear. But for the other three, we actually don't know what can happen. So it depends on how fast those functions gonna go. So depending on the rate of the function. If fx go faster, you get one result. If gx go faster, you get another result. But if they go comparatively in a similar rate, you can get like even a finite number. So we can study those kind of things in this one. So that means we can study 3 different type of indeterminate forms in this one. So there are 2 ways to handle a problem like that. There are 2 ways, but you know that from our log derivatives problems, when you have a power function, when you have like a function of a function, like a function to a function powers, what we normally do is we use the log approach. We take the natural log. Once you take the natural log, you can see that this power term going to come in front because it's going to be a product. So that's the kind of idea to solve a problem like this. So, and then also we can use another result from pre-calculus to solve this problem. So those are the 2 different types to do it. So let's talk about the first type. So method 1. So in method 1, what we normally do is we're going to let y equal the given expression. So whatever the expression, we're going to call that y. So that's the starting point for these problems. Once you do that, then what we do, we take the natural log of both sides. We normally call ln. So we take the natural log of both sides. And once you take the natural log, on the right hand side, you can see that you can use the what they call the power out rule. Power rule means you remember this result. When there's a power ln x to the p, you can see that the p can come out as a multiplication factor. So that's like a power. If there's a power, it's going to come out. So what we normally call power out rule. So using the power out rule, actually we can simplify it. So the power goes away and it simply become a multiplication. So it's like a and then once you do that, you can see your problem going to be type 2 indeterminate form. From type 4 it become type 2, and after you go to type 2, which are the the products, and you can use the type 2 techniques to do the rest of the problem. So and then what we're going to do, we're going to find the new limit. You're going to find the new limit. Still the same limit, like x goes to whatever the 0, 0 plus, infinity, whatever, we still the same thing. And so you will get a number here, and then what you can do, you can convert that using the you can convert that from the log form to the exponential form. You can convert that to the exponential form, and this is the rule that we use. We know that if ln y equal a, that means you can write y as e to the a, because ln means the base is e. So that means you can write y equal e to the a. So that's the kind of idea. So so that's like a main result we're going to use for to solve a problem like that. So there are 4 steps to do a problem like this. So you take y equal expression, take the natural log, the second step, and use the power rule to simplify, and then find the new limit. Once you find the limit, you're going to convert that into the exponential form, and then you get the answer. So let's try to look at a problem and see how this is going to work. So we're going to look at this problem. This is like one of the interesting problem in these kind of ones. So find the limit when x goes to 0 plus, that means goes to 0 through larger values, through positive values, x to the x power. So let's see how we can do this problem. So we can follow those 4 steps. So the first one is we can let y equal x to the x. So let y equal x to the x. That's the first step. And the second step we can take, so we can write those things. Take natural log, we just say ln. Take natural log of both sides. Both sides. So when you do that, on this side it's clearly ln y. The other one is also ln x to the x. Using the power rule, the power gonna come out. So that means it's gonna be x and then ln x. So see what happened. So that means right after we do that, the power simply becomes a product now. So we have the product. Now what we're gonna do, we're gonna take the original limit. So we can do the original limit. What's the original limit? In the problem you can see is a limit when x goes to 0 plus. That's what we're looking for. We do the same thing. Ln y. So on this side again we take limit when x goes to 0 plus x ln x. So now when you do that, let's review the graph of natural log. So remember the graph of natural log is like that. So that means when x goes to 0, you can see the function goes to ln goes to this ln x. Ln x goes to negative infinity. And this one, first one goes to 0. So it's a 0 times infinity problem. 0 times infinity problem. So if you have a 0 times infinity problem, what you want to do, before you take the derivative, you have to convert that into 0 over 0 type. So what we normally do, we're going to find the easy one and divide by that. So that means limit when x goes to 0 plus, we can write this one as dividing the top and bottom by x. You can write this one as 1 over x. And right after we do that, you can see this is a infinity over infinity. We don't write negative infinity, I mean it's infinity. Infinity over infinity problem. So negative infinity over infinity problem. We just say infinity over infinity problem. So it's infinity over infinity problem. So, and then what we can do now is we take the derivatives now. So we take the derivative now. So, so once you take the derivative, see what happened. So, so you remember the derivative of natural log is ln x, 1 over x. So we know that the derivative of ln x is 1 over x. So we can use that result here. So that means, so it's the same limit x goes to 0 plus 1 over x. The bottom, you can see that you can write 1 over x like this. 1 over x you can write as x to the negative 1. That means when you take the derivative, it's going to be negative x negative 2 using the power rule. Or you can write this one as negative 1 over x squared if you want. So that means you can write this one as negative 1 over x squared. So that's what happened when you take the derivative. So now what we have is the algebra. So this is actually very easy to simplify. What we normally do is we can pull the negation out. That's one thing. So we're going to multiply the top and bottom by x squared. The goal is try to get a 1 for the denominator. That's what we're trying to do. So to try to cancel the denominator term. So you multiply by x squared the top and bottom. And once you do that, this is what you get. So you get limit x goes to 0 plus ln y equal negative. I pull the negative sign out. And you can see it's going to simplify to simply x. Now when x goes to 0, and you know that this is going to go to 0. So we found the limit. So the fourth step is to convert this into a natural log to the exponential form. So that means the next one is what we can do is we can write limit x goes to 0 plus y, which is equals to limit. Actually, it will be better to write it like this, to x to the x, that's what we're looking for, which is equal to y, limit when x goes to 0 plus, but y means, you can see this is the limit. So when you isolate y, using the result, remember what we had was when you have ln y equal a, if and only if, this means that y equal e to the a. So we use the same idea here. So that means, so in this limit, what will happen is when you isolate y, this is simply going to be e to whatever the limit that you get. So e to the 0, that means it is 1. So the answer is 1 for this problem. So if you need to know what exactly happened here, what we do is we write this one y like using this result. Remember we can write y like e ln y. So this is a pre-calculus result. So you can always write it like that. And then what we know is, we know this e and ln x, those functions are continuous in their domain. So we can bring the limit inside. So that means what happened here is, in the next step, this is what happened. Limit x goes to 0 plus y. Now I bring the limit inside e and then inside ln. So what happens? So we can write this on e and then we bring the limit inside. So limit x goes to 0 plus ln y. So you can see that this we already know. That's what we found. So this is 0. So that it's going to be e to the 0 because we found that. So that's exactly the steps for this problem. So that means we use the continuity of the exponential function. So we use continuity. Use continuity of the ex function. So that's the reason why we get this one. So in the you can see in the when we do the second method, actually this is exactly the result that we use. So we can use this directly without taking natural log. So that's the second method actually. So but it will be clear when we do that. But this is exactly what happened here. So that's the logic here. So once you find the limit, that means this one. So you're going to put that as the power of e. That's how the conversion works. So that's the conversion formula. Okay. So let's look at another one. So let's look at this problem. So we have limit when x goes to 0 plus 1 plus sine 3x to the power cotangent 2x. So this is a trigonometric problem, and you can see that when x goes to 0, since sine 0 is 0, we know sine 0 is 0, and the cotan function approach infinity, one of those infinities. So what we have here is, you can see that the sine goes to 0, so you get 1 to infinity situation. So when you have 1 to infinity situation, this is an indeterminate form. So we're going to use the fourth step for this one. So we're going to let y equal the given function 1 plus sine 3x to the power cotangent 2x. The next step is take natural log. So we take the natural log of this one. So once you do that, you can see the power comes out. So I'll write that step here. And then times the natural log of the function. Now after we do that, and you can see now we take the original limit. The original limit is limit when x goes to 0 plus ln y. So we're going to simplify the other side. So it's a limit x goes to 0 plus cotangent 2x times ln 1 plus sine 3x. So what happened when you do that? We know that though we did not change those functions, so we just switched the terms. So interesting thing happen is, remember last time we know that this one goes to 1 because of, we know that ln 1 equals 0. So that's like one of the reasons why this happened. So because of this goes to 1, so you can see this product actually goes to 0. Product goes 0. And then cotangent still goes to infinities. So this is an infinity times 0 problem. So this is going to be a infinity times 0 problem, and we know how to do infinity. That's a type 2 Bernoulli. So what we're going to do is we're going to convert this into either 0 over 0, infinity or infinity. So the easiest thing that we can do is we can bring this term down, but we know the cotan is 1 over tangent. So we know that. So we know that cotangent theta is 1 over tan theta. So because of that, what we can do, we can bring this down. So we can write this one as limit x goes to 0 plus, we can write this one as limit natural log 1 plus sine 3x divided by tan 2x, because cotangent is 1 over tan. Now right after we do that, and you can see that this is a the top is going to be 0, the bottom is also 0, so it's going to be a 0 over 0 problem. That's like a type 1. So you can see from type 4 it went to type 2 and then go to type 1. Very interesting. Okay, now what we need is take the derivatives. So let's take the derivative and finish the job. So I'm going to write it now. Before we take the derivative, let's recall one of the results. So one result is if you take the derivative of natural log, you get 1 over x. And the other result is if you take the derivative of tan x, so it's going to be secant squared x. So we can use those two results here. So that means there is going to be limit. So again, the reason is it is a 0 over 0 problem, type 1. So x goes to 0 plus. So when you take the derivative, you can see the function goes down. It's a chain rule. 1 plus sine 3x, and then multiply by the derivative of the inside function, which is the cosine 3x, and then times the inside function is 3. So that's what you get for the derivative of the top. Derivative of the bottom is simply a secant square 2x times 2. So this is like how we use the chain rule for this problem. So if you are not familiar with the chain rule, and look at the link in the description to learn like how to do a few things like this. So now let's you can see you can pull 3 over 2 out of the limit, and then once you do that, and you can see that all the other terms actually goes to, when x goes to 0, you can see this term goes to 0, this term goes to 1, and this also goes to 1 because secant is 1 over cosine. Since secant is 1 over cosine, we know that secant is if you take the cosine x, 1 over cosine is a secant. So that means if one goes to 1, the other one also goes to 1. Since this cosine goes to 1, secant goes to 1. Actually it's not 0, so it goes to 1. So that means all those terms goes to 1. So because of that, you simply end up getting 3/2 as the answer. So that's the answer for this limit. It's like very interesting one. So we got as limit x goes 0, 1 plus sine 3x to the power cotangent 2x equal 3/2 as the answer. You can see the 3.5. So those two are the numbers actually. So those two numbers go as a fraction. Very interesting. Okay, so let's look at the next method. So the second method. So in method 2, the major result is this one. So we're going to recall this important result again, x equal any number you can write as e ln x. Only assumption is x has to be positive. If x is positive, we can use this. So that's the major result for the second method. And we also use the same method to explain one of the result earlier. So the steps are these. So we have these 4 steps. So the first one is rewrite the problem using this new property. So we replace the expression by e to the ln the expression. And then we use the power out formula or power out rule to simplify, because the power going to come out because of the power out rule. And then we can use the continuity of y equal ex. We know that y equal ex is a continuous function, so you can bring the limit inside. So you can bring the limit inside. After you bring the limit inside, it's going to be either type 1 or type 2. So you can use the type 1 or type 2 method to find the limit of the inside function. Once you do it, you get the answer. So let's try to look at this method using several problems now. So we have when x goes to 1 plus x to the power 1 over x minus 1. So when you have that, so you can see that this is going to be 1 to infinity, because you can see when x goes to 1 plus x minus 1 goes to 0 plus. So this is going to be 0 plus. It's a positive, small positive number. That means 1 over means it's infinity. So it's a 1 to infinity problem. So that means what we do according to the second this new method, we are not going to take the ln part here. So what we normally do, so we use the result, so that means we're going to rewrite it. So it is a limit. I'm going to add all these steps here just to make sure that you understand what's going on. And then we rewrite this. So it's a e to the ln, the same expression, x over 1 over x minus 1. And then this is the power term that's going to come out using the power out formula. So it's the same limit. So we are going to find the limit yet. E, so it's going to come out. So it's going to be 1 over x minus 1 ln x. So if you want to rewrite it like little exaggeration, you can write it like this first. So it's a limit x goes to 1 plus e, you can write this one as ln x divided by x minus 1. See exactly what happened when you do that. You can see in the first form, when x goes to 1 plus, ln x goes to 0, 1 of x minus 1 goes to infinity. So it's going to be an infinity times 0 problem. But when you put it in the denominator, you can see that this is a 0 over 0 problem. So it's very interesting. You just transform from type 2 to type 1 right there. So you can see this is the type 2 problem and this is the type 1 problem. So it's very interesting what happened. Now you can see that you can just use the Bernoulli because it's type 1. So we take the derivatives now because inside what we have is a infinity times 0, and then inside what we have is a 0 over 0. So we use the derivative step now. So we can take the derivatives for limit x goes to 1 plus e. When you take the derivative, ln derivative, we know that is 1 over x, and then actually before we take in the find the derivative, you have to bring the limit inside. So because after that we can take the derivative. So I'm going to write the next continuity step. So I'm going to bring the limit inside. So let's do that. You can see now what will happen at this stage. You can take the derivative. Earlier you cannot because it's not in the right format. So now we take the derivative of the inside function. So that means we have e ln. So it's very important where you write the limit. Outside you cannot. It's be inside. And then once you take the derivative of ln, which is 1 over x, and the bottom simply become 1. So you can see that when x goes to 1, 1 over x goes to 1. So the answer is e to the 1. E to the 1 means e as the answer. So you get e as the answer for this interesting problem. So it is limit when x goes to 1 plus x to the 1 over x minus 1 actually goes to e. So it's very interesting. And there are a few other expressions that you're going to get e or some other versions of e. So I'm going to give you those, and then why don't you try them as practice problems. So let's see them. Let's do one more celebrated one. That's like a very interesting one. So let's do that first, and then I'm going to give you the rest as exercise problems. So we have limit n goes to infinity 1 plus x over n to the nth power. So this problem may be slightly different from what you had earlier. Here we have n like normally an integer. They are discrete, but let's assume it is a continuous variable, because otherwise we can't take the derivative. So we assume it is a continuous variable. So we're gonna use derivatives for this one, like assuming it is a continuous variable. So we can use the same approach as before. So what we can do is we can write this one using the limit n goes to infinity, e to the ln, the expression 1 plus x over n to the n, and because of natural log, the power comes out, so it's going to be e n times ln 1 plus x over n. Now what we can do, we're going to bring the limit inside using the continuity. So you need to do that before you take the derivatives. So it is n times ln 1 plus x over n. So let's see what happens when n goes to infinity. When n goes to infinity, you can see the first term goes to infinity. And the second term, x is like a constant, just a fixed number. And you can see n goes to infinity. So that means in this one, so you can see this whole term goes to 0. This goes to 0, ln1 goes to 0 because we know the ln1 going to 0. ln1 is 0. So it's a 0 infinity times 0 problem. So when you have an infinity times 0 problem, what we do, we're going to bring it to either 0 over 0 or infinity. So we do that under the limit. So it's e limit n goes to infinity, and then we can write this one as ln 1 plus x over n, and if we divide by the top and bottom by n, so it's going to be 1 over n. Now we take the derivative. We assume n is a continuous variable, so we take the derivative. So once you take the derivative with respect to n, not xn, so what will happen is you can write this one as e limit n goes to infinity. For the top, we have this a chain rule, so it's a 1 over the expression. Remember, we are taking derivative with respect to n. So that means it's a 1 over n, that means it's going to be negative 1 over n squared. And the bottom is also negative 1 over n squared, actually times x, so there's an x term also, because x is a constant now. So that's what you get. Now let's see what will happen, and you can see that these two terms get cancelled out. So these two get cancelled out. So when n goes to infinity, since x is a fixed number, you can see that this term goes to 0. So this term goes to 0. That means you get just a 1. So 1 times x. So you simply get now e limit n goes to infinity 1 time x, so you get x, but x is fixed now, so that means the final answer is e to the x. So that's how you use the Bernoulli rule to show that the special limit is actually ex. So I'm going to write this as a result because this is very important for you in the future. So we have this result. So remember this result. This is very useful, and we can use in multiple times. But this is how you prove it. So you use the Bernoulli rule to guess the result, and we use the version 2 for this one. So let's try to look at one more problem. Actually, now try to see whether you can prove these two results as exercise. So we have limit x goes to 0 plus 1 plus x to the 1 of x. Now here x is the variable. So you're going to get e in this, the first one. In the second one, it's like very interesting one. It is a limit when x goes to infinity 1 plus a over x to the bx power. When you do that, here again x is a variable, you should get e to the ab. So these are really interesting problems, and see whether you can do that. So you can use either method 1 or method 2. They are very similar. Only the length is a difference. So see whether you can get the answer. So we're going to do maybe just 2 more examples just to kind of finalize this one. Let's do another trigonometric one. So we have limit x goes to 0, cosine x to 1 over x squared. And we know the cosine graph. According to the cosine graph, when x goes to 0, so you can see it's going to 1. So 0 close to 1. So this is a 1, 2. When x goes to 0, 1 over x squared goes to, x squared goes to 0, but 1 over goes to infinity. So it's a 1 over infinity problem. So it's an indeterminate form. So again, we use the method 2 here. Limit, so it's a e. What we do, we can bring the limit inside because you know this step now. So we can bring the limit inside, and we can write this one as ln cosine x to the 1 over x squared. So I skip the first two steps because you know this is what happened, right? Because e ln x, and then you can bring the limit inside. Now you can see, so you're gonna bring the power in front, power term in front. So you can write this one as e limit x goes to 0, 1 over x squared ln cosine x. So again, remember this is like there are different type of arguments. You can bring the x squared actually underneath, because that's you're gonna give you one step closer when you do that. So you can directly write it. So ln cosine x, you have to write this underneath there. So then when you do that, when x goes to 0, you can see this is a 0 over 0 situation, because ln cosine goes to 1. When cosine goes to 1, ln cosine goes to 0. So it's a 0 over 0 problem. So we can take the derivatives now according to Bernoulli. So limit x goes to 0. So take the derivative, and we know that ln means 1 over, so we can write this as 1 over cosine x times sine x. It's a negative sine x actually, negative sine x. And then divided by, in the bottom you get 2x. Now we can rearrange some of the terms, and you can see that you can pull the negative sign in front. So there are a few things that we can do, and also we can see that when x goes to 0, cosine goes to 1. That means we can ignore that term. So that means we can write this one as, this is exactly same as e negative the limit x goes to 0. You can see that this is simply sine x over 2x. So, and then you can see this is again when x goes to 0, it's a 0 over 0, and this is actually, we prove this one in the type 1 results. So but if you forget that, then we can just take the derivative again. So it is e negative limit. So let's take the derivative. Once you take the derivative, you get this sine become cosine and 2x become 2. Now actually take the limit when x goes to 0. So when x goes to 0, you can see that it's going to be e to the negative 1/2. So 1/2 power means, negative 1/2 power means 1 over 1/2 power means square root. So it's 1 over square root e. It's like very interesting. So 1 over 1 or 1 to infinity problem become 1 over square root e. It's very interesting. So let's do the first problem using the second method now, just to complete the argument. The first problem using the second method as the last one. Actually, let's slightly change the problem. You can try that later. So let's try to do this one instead. So when x goes to infinity, because we could not do any problem of this type. So you can see x goes to infinity, 1 over x goes to 0. So this is also a indeterminate form, because we don't know which one gonna win. So we again use the second method. So it is e, we can write the limit, we're gonna bring the limit inside, and then we have ln x to the 1 over x. You can skip some of the steps because you don't know what's going on right now. So e, the limit x goes to infinity, so x comes out, so it is so you can write this one as again we can put the 1 over x in the denominator, so you can write this one directly ln x over x. We know this step now. So right after this happen, you can see this is a infinity over infinity problem. So it's a type 1. Since the type 1, what we're going to do is just take the derivatives. So it's the limit x goes to infinity. If we take the derivative is 1 over x to 1. So it is so simple now. So when x goes to infinity, 1 over x goes to 0. So you can see this limit is simply 0. So that means it is e to the 0, which is 1. So you get 1 as the answer for this problem. So it's very interesting. So we use the method 2 for this problem. You can use the method 1, but this is method 2 is very quick. Okay, so thank you so much for watching. And so we did all three, all four types. So it's a Bernoulli type 1, 2, 3, 4. The first type was 0 over 0 or infinity over infinity. That's type 1. Bernoulli type 2 is 0 times infinity. So when you have 0 times infinity, you convert that into 0 over 0, infinity over infinity. It doesn't matter which one. The Bernoulli type 3 means infinity minus infinity. And when you have that, what we did was we just use algebra to simplify first. Once you use algebra, what will happen? That problem will convert to one of those forms, infinity or 0 over 0. And as the last one, what have is we have those power limits. So it's a function of a function. So there are powers. So in your powers, the three things can happen. It can be 1 to infinity, 0 to the power 0, or infinity to power 0. So if you get those three, those are what we call indeterminate forms. So there are two ways to do it. Either you use the log, you take the log, or you use the special pre-calculus result x equal e to the ln x. I mean, if it is like a long problem, it may be good to use the log one, because then you don't have to write much. But if it's a short problem like the last one, it may be easy to use the exponential version because there are no much writing. So yeah, so if you do the easy one, we normally use the exponential one. If it's a long expression, we can use the log form. So that's how we kind of know which one to use. Okay, so again, thank you so much for watching. And then now what you can do is you can try those practice problems that I have given in the description. So thank you.